Okay, good afternoon, everyone. I'm Hongyi Li, and this presentation is about interactive dialogue learning. And the PI of this project is Richard Tsai, and unfortunately, he cannot be here with us, so I'm going to do the presentation. Our champion is Prof. And this is the outline of today's talk, and I do not have to remind you how important it is if the machine can interact with human by natural language. But to have a dialogue system, there are at least five modules in the dialogue system, including speech recognition, spoken language understanding, dialogue management, language generation, and speech synthesis. We are going to talk about our recent progress in these 5 fields. And all of our achievement is based on the state-of-the-art deep learning technology, including reinforcement learning or generative adversarial network. And I will start with spoken language understanding. So when it comes to spoken language understanding, when it comes to understanding spoken content, first thing comes to my mind or comes to every non-native speaker's mind is TOEFL listening comprehension. So we want to know that if we ask today's state-of-the-art deep learning technology to test TOEFL listening comprehension, what kind of degree can it obtain? So this is TOEFL listening comprehension. Machine has to listen to the audio story, which is about 5 minutes long, and it will see a question, and there are several choices, and hopefully the machine can select the correct one. The question we provided to the machine is exactly the same as the ones that human tester will see in the real exam. So basically, if you want to solve this problem based on today's deep learning technology, what you need is a neural network. I believe everyone in this room knows that neural network is actually a function. Input something and output something. In TOEFL listening comprehension, the input of the machine is a question, an audio story, and the choices, and the output is the answer. And to learn this kind of network, of course, you need some training data. Where can we have the training data? There are some previous exams you can collect from the internet. So you can use this previous exam to train a neural network for TOEFL listening comprehension test. This is the model we use. It's kind of complicated, so we are not going to describe it at this moment. By the way, we proposed this model and attend the movie QA competition, and we won the second place. And this is the result we can obtain. Before use machine learning technology, we implement some trivial approach to see what's the performance we can obtain. Because probably there are some serious flaws in TOEFL listening comprehension test, so probably there are some very naive approach can obtain good result. But unfortunately, none of the naive approach can get good results, so it looks like TOEFL listening the question of TOEFL listening comprehension tests are well designed, so the best naive approach can only achieve 35% accuracy. Then we apply some machine learning technology, and as the time goes, we can get better and better performance because we modify the architecture of the network, and eventually we can get 55% accuracy. Of course, around 50% accuracy is not actually very good. If you only can get this kind of score, you cannot get admission at the top score in the University of US. But however, if your friend cannot get this score, you can laugh at him. So this is what I can do based on this study. And besides that machine tech TOEFL listening comprehension, now we have another ambitious goal. We build a new task, we build a new corpus called spoken squad. If you know what is squad, everyone have working on natural language processing know what is squad. You can immediately get what is spoken squad. It's the speech version of squad. And you can find the data and our paper on the links on this slide. I'm not going to go through the detail here for time limitation. And on spoken language understanding, besides question answering, we're also working on dialogue state tracking. In dialogue state tracking, machine have to given some utterance, machine have to do know the information in the utterance. For example, machine has to know that if this is a restaurant booking system, machine have to know that the food the user want to eat is Chinese food and the price range is moderate, something like that. And in the real application, the input of the user is utterance. So you need an AS assistant to first transcribe the utterance into text. However, in the noisy environment, the transcription can be very poor. And the poor transcription, of course, lead to very bad dialogue state tracking result. This is a real example. When the system said, what kind of food do you want? The user has some response, then the output of the AS assistant is which for. Can you guess what the user wants to say? I believe no one can guess what the user wants to say. So if human cannot get the result, machine cannot get the result either. Then, however, in the speech recognition system, the speech recognizer can not only recognize one transcription. It can recognize all the suspected hypothesis results. Usually, a speech recognition system will only return the hypothesis it has the highest confidence. But we can also ask the speech recognition system to return multiple hypotheses. So here we ask the speech recognition system to return the top 5 hypotheses. Then based on the transcription, based on the top 5 hypothesis transcription, you can find that there's a word French. So actually, what the user wants to say is French food, but it's misrecognized into which for. So if we can let the DST system, a dialogue state tracking system, exploit all the possible hypotheses, of course, we can get much better result for dialogue state tracking. But how can we achieve that? If dialogue state tracking system only simply take all the hypotheses as input, then there's not lots of noise in all the hypotheses. But if DST system can only pick one of the hypotheses, it does not know which one it has to pick. If it's just simply pick the one with the highest confidence, it's which for, then it cannot get the correct result. But until now, there's not a good way to let the DST system to pick the best hypothesis, the hypothesis which is most suitable for dialogue state tracking. So our idea here is we want the machine automatically learn how to find the best hypothesis, which is most suitable for dialogue state tracking. And because this problem is non-differentiable, it's kind of complicated, it's not a typical neural network approach, you can use backpropagation to learn it. So we formulate it as a reinforcement learning problem. And I'm not going to go through the detail here due to time limitation. What I only want to show you is, this is a typical deep reinforcement learning introduction. So you just keep in mind that we use this reinforcement learning to solve the problem of dialogue state tracking if there are speech recognition errors. And we already submit the paper to this interspeech, and this is the result we can obtain. We just look at the right table. In the right table, here we show the result of the top 10% largest word error rate utterance. If the word error rate is very large, of course the performance will be very poor. You can find that based on this table, if we only consider the top 10% largest word error rate utterance, based on the typical approach, the accuracy you can obtain is 47.7%. However, with the proposed approach, we can obtain 63.1%. So there's absolutely around 15% improvement based on this approach. If the machine can learn to exploit, leverage the multiple hypotheses in an intelligent way. So besides spoken language understanding, I'm also going to talk about dialogue management. So after machine can understand the spoken content, then it has to decide which action should it take to interact with the human. Then this is dialogue management. I'm not going to go through the details of the dialogue management, but everyone probably knows that to learn a dialogue manager, a very typical approach is you use deep reinforcement learning. You hire or you have lots of users, and you ask those users to interact with your dialogue manager. Interact probably millions of times, and based on the deep reinforcement learning approach, the machine will learn how to maximize the reward it can obtain, and eventually it learns how to interact with the users properly. However, in practice, this idea doesn't work. Why? Because humans are very busy. No one can interact with your system millions of times to help you train the system. So there's a very common solution. widely used in the literature, but not many people know, is you handcrafted a rule-based simulated user. Based on some rules, you have a simulated user, and you use this simulated user to interact with your dialog manager. And because the user is simulated, you can interact, your system can interact with the user as many times as it wants. And in this approach, of course, you can train a dialog manager by deep reinforcement learning. Of course, the problem is the users are rule-based. They are not real users, so their behavior with respect to the real user would be probably very different. And usually, the solution is during the presentation, you tell the audience that, look at our dialog system. We use the most state-of-the-art deep reinforcement learning approach to train our dialog system just as AlphaGo. So it's very poor. And for user part, you just have one slide describe, say it is simulated user, but due to time limitation, we just skip this slide. So no one will pay attention on that. But actually, this is not the best idea. Because here you have to design your simulated user, you have to handcraft it, and you use the handcrafted user to train your dialog system. If this is your setup, probably directly handcrafted your dialog system is much faster than have a handcrafted user first. So probably this is not the best idea. So now we come up with a new idea. In this new idea, we believe we can simultaneously train a simulated user with the dialog system. So both the dialog system and our simulated user are trainable. So they can interact with each other, and both of them can update their parameter to achieve the best performance, to achieve the best reward they can obtain in the test, and both of them can improve based on each other. So this is the basic idea. So we replace rule-based simulated user with a simulated user that can be learned from the dialog system. And the simulated user and the dialog system can learn jointly. This figure is kind of complicated. In this figure, I just want to say that at the right-hand side, this is a dialog system, and at the left-hand side, we have a user simulator. Both of them are neural network, and they are learned from the interaction. And here we apply this technology on interactive spoken content retrieval. This machine can help the user pick the desired content from a large spoken database. And this is the result we can obtain. I think probably last year I have to present some result that is based on the rule-based simulator, and fortunately no one asked about that. Then in the upper part, this is the result using simulated user. In part A is the result based on rule-based simulated user. And on the right-hand side, you can see some return. The larger the value means better the performance. And now we replace the rule-based user with the trainable-based simulated user. So the results are shown in part B and part C, which is at the lower part. And you can find that the result we can obtain is much better. If the user is trainable, we can get much higher reward. So this is about dialogue management. And then I'm going to talk about natural language generation. So here, what we want to have is a personalized chatbot. So as you know, a general chatbot only generate plain response. However, we talk in different style, and human will talk in different way, in different style to different people in different conditions. So we want the response of chatbot can be controllable. We want the generated sentence, the generated response can be controllable. For example, if the input question is, how was your day today? And the machine has to give a response. But if the machine, your chatbot is in different mode, it will respond in different way. You can assume that it is in a positive mode, then its response will be, it is a wonderful day. On the other hand, if it is in a negative mode, then its response would be, it is a terrible day. Then in the future, probably we can let the machine determine which mode it should be in based on the environment. in this way, we can have a personalized chatbot in the future. The chatbot can be in different mode. When you talk to different people in a different situation, then given the same question, it can respond differently. Then personalized chatbot would be available. And today, what I'm going to show is just a very small step toward the personalized chatbot. What we want to build is a positive chatbot, a happy chatbot, an optimistic chatbot. Its output is always a positive response. Based on exactly the same technology, we can also build a negative chatbot, but we are not motivated to build that. And to achieve that, to achieve controllable response output, we found that there are two possible ways to achieve that. The first way is you have a chatbot, and you modify the parameter of the chatbot to make its output always become positive. Another way is you have an off-the-shelf chatbot. You cannot modify its parameter. You fix its parameter. But you learn another transformation network. The transformation network takes the output of the chatbot as input and transform the output into a positive response. So no matter what the chatbot say, transform that into a similar meaning sentence, but it's positive. So there are two ways to achieve that. And for each type of approaches, we will introduce two methods. So for the first type of approach, we'll introduce persona-based approach and reinforcement learning. And for the second type, we will introduce plug and play and cycle gain. So the first approach I'm going to introduce is persona-based model. And this is the type 1 approach. So the parameter of the chatbot will be modified based on this approach. So this approach works like this. During training a chatbot, you will have training data like this. You will tell the machine that the input is how is today, and the reference output should be today is all set. Then there is a sentiment classifier. Today it's very easy to have an off-the-shelf sentiment classifier. The sentiment classifier takes a sentence as input and output a scalar. This scalar represents how positive the input sentence is. Then you take the reference response as the input of the sentiment classifier. And because today is also positive, so the output value is 0.9. We assume 1 is the largest value it can obtain. So it's very positive. Then the decoder take this value, take the output of semantic classifier as input, and output a response. And for another example, if the reference response is negative, then the output of sentiment classifier will be negative. Then the decoder takes a negative value to generate the response. Then during the testing time, the user say, I love you. Then you can give the decoder different value. Originally, this value during the training time is from sentiment classifier. But during the testing time, you can control this black value. Then your machine, your decoder, your chatbot will have different kind of output. For example, actually, this is a real example. If you set the value as 1.0, the machine will output a positive response, which is, I love you too. If you set the value like 0.0, the output will be, I'm not ready to start a relationship. But this is just for you. It can start a relationship with others if he wants. So this is not what we want. So during the testing, we want the chatbot always to be positive. So we will set the value to be 1.0 during the testing time. This is persona-based approach. Then the second approach we use to modify the parameter of chatbot is reinforcement learning. In reinforcement learning, we also need a sentiment classifier. And the sentiment classifier takes the output of the chatbot as input and output a value. Then this value is the reward of your chatbot. You consider your chatbot as an agent, and the reward you obtain is the output of the sentiment classifier. Then your chatbot will learn to maximize the output of the sentiment classifier. And as you know, when sentiment classifier output large value, that means the output of the response has a large parameter. So the network will, your chatbot will update its parameter to have a positive response in order to get large value from the sentiment classifier, in order to get large reward from the sentiment classifier. So this is the second approach. Then for the third approach, we are going to train a transformation network, input a response sentence, then it will transform it into a positive one. The first approach we use is called plug and play. This is an approach borrowed from image processing. And the idea is like this. We have an autoencoder, and we train an encoder and a decoder here. For the encoder given a sentence, it will represent the sentence as a code, represent the semantic meaning of the input sentence, and the decoder can take a sentence and the decoder can take a code as input and generate the output response. Then to transform a general response into a positive one, the idea is given the response of the chatbot, and the encoder generate a code. Then you modify the code. I will tell you how to modify the code. Then you modify the code. Then the decoder take this new code as input and generate another response, and hopefully it can be positive. Then how can we modify this code? There are two constraints for this modification. There are two directions for this modification. The first direction is you want to modify this code from the blue one to the green one to make the output sentence has a large output based on the sentiment classifier. You want the output of the decoder to be a positive sentence that it can obtain large score from your sentiment classifier. But at the same time, you don't want the blue code and the green code to be too different, because if they are too different, then you transform a sentence into a completely non-related sentence. This is not what we want. So we want the blue code and the green code to be as close as possible. In this way, the input sentence and the output sentence of transformation network will probably be semantically related, but the output will be more positive. Don't worry if you cannot 100% understanding this approach, because it doesn't work. So let's just skip it. So for the fourth approach, we use cycle gain. I'm not sure whether the audience familiar with the technology of cycle gain. So for the gain technology, I give a very, very brief introduction. Today, based on the technology of cycle gain, if you have two domains of data, you do not need the relation between these two domains. You do not need the pair data between these two domains, but you can train a transformation network to transform the object in one domain to the object in another domain. For example, given, this is a very typical example. Let's see the most upper example. For example, given some real photo, you can transform it into the painting of Van Gogh. You transform it into the painting which is styled like Van Gogh without any pair data between the X domain and Y domain. So here we just apply this idea. So we have some positive sentence considered as X domain. We have some negative sentence considered as Y domain. And based on the technology of cycle gain, you can directly learn a transformation that will transform between these two domains. This is just the framework of cycle gain. You can use it to transform image. And you can also use exactly the same idea to transform the negative sentence to be a positive sentence. There is something probably worth mentioning. Because in natural language, the sentences are discrete. The word tokens are discrete. So if you put it in the network, you cannot directly differentiate the whole network. To deal with this problem, we use word embedding to represent each sentences. So instead of using a set of tokens to represent an sentence, we use a sequence of vectors to represent a sentence. So this is how we adapt the image processing technology to natural language processing technology. So this is the result we can obtain from cycle gain. It can transform negative sentence into the positive one. So here, when I say I miss you, it output I love you. I say I don't love you, it output I love you. I say I cannot do that, it output I can do that. I say, here's a good one. I say, sorry for doing such a horrible thing. It outputs thanks for doing a great thing. Of course, it sometimes makes some mistake. I say my doggy is sick, then the output is my doggy, which is ridiculous. And this system is very useful. So if your boss is always very mean, you can put this system in your earphone, then you will be happy. And here is some experimental result. Here the result we show is human evaluation result. We also have objective evaluation result in our paper, but the result is just very similar, so I do not show the objective evaluation result here. So here what I show is the human evaluation result. We evaluate the result from 3 different aspects. So first of all, because we want the output of chatbot to be positive, so we ask the user whether you think the output of the chatbot is positive or not. So this is the first question we ask the user. Then the second one is we don't want the output to be just positive, because the chatbot can do something like always just output some random positive word, like good, 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 then the sentiment classifier, human will think it's positive, but it's not reasonable. Its grammar is very poor. So we still have to ask the user, do you think the output of the chatbot is grammatically correct or not? Then the third question we ask is, only check the sentiment and the grammar is not sufficient, because the chatbot can always respond a sentence like, it is a wonderful day. It's positive, its grammar is correct, but this is not what we want, because the chatbot should have different answer based on the user input. Then the third question we ask the user is, do you think the chatbot output a suitable response corresponding to the input? And here, I'm not going to go through the details of the annotation. Here, in this table, larger the value means better the performance. And 1.0 is the largest score you can obtain based on the human evaluation. So let's take a look at the first column, which is for sentiment analysis, which is for whether the output of the chatbot is positive or not. So we found that the first two approach can have more positive reward, can output more positive sentence, and the last two approach cannot output the sentence as positive as the two approach. So it looks like, because the first two approach will directly modify the parameter of chatbot instead of just transform its output, it looks like directly modify the output of the chatbot can make the output response more positive. Then here is the grammar. First of all, you can find that the baseline, the first row, is the result of the baseline. The row label with sequence to sequence is the baseline. And you can find that the grammar of the baseline is completely correct. The user cannot find any error in the baseline model. And we can find that, compare the full approach for sentiment controllable chatbot, reinforcement learning and CycleGAN get the best performance. They make less grammatical error compared with the other two approaches. Then the last column, we show the result of semantic coherence. And here, based on the result, we found that, of course, the original chatbot is most sentiment coherent. But the second one is CycleGAN. The sentiment coherence of the CycleGAN is better than the rest three approaches. So this is what we found based on the human evaluation result. So it looks like, based on the result, both reinforcement learning and the CycleGAN work pretty well compared with the other approaches. Then here is some example. So this is the real example in the experiment. So when I input, I'm just less interested in the how-to and more in what and why of the thing we build. And for the original model, its output is not a good idea. The user probably not happy about that because he or she is negated. Then for persona-based approach, it output I'm interested in this. And RL, it output is a good one. So both the output are positive, but different from the original output. Then for plug-and-play approach, this is interesting. It just replaced good with wrong, so the output is not a wrong thing. And for CycleGAN, it just removed not, so its output is a good thing. Here is another example. The input is always learning and self-improving is a huge turn-on for me. Then the sequence-to-sequence model says, I'm not sure if I can see you in a relationship. So the user will be very unhappy if he or she sees this response. Then for plug-and-play, as I have mentioned, plug-and-play doesn't work. It usually generates some very ridiculous sentence with lots of grammatical errors. So it outputs something like, if I can see you special, I'm not sure what it want to say. And for CycleGAN, it just removed not. So it say, I'm not unsure if I can see you in a relationship. This sentence kind of weird. And for persona-based approach, it say, have a word with your mother. So this is just completely ridiculous, completely random. I don't know why it output in this way. And the output of reinforcement learning is I love you so much. So the user will be very happy for this response. So this is basically what I want to share with you for natural language generation. Then I'm going to talk about speech recognition. And I know everyone is very familiar with speech recognition. So for speech recognition, to train a speech recognizer today, you have to collect a large amount of data. And there's lots of state-of-the-art model. You can train a speech recognizer end-to-end, input the speech signal, output a word sequence, then that's it. There are lots of models can achieve that, for example, sequence-to-sequence model and CTC. However, to train this kind of model, you have to collect a large amount of data. You have collect large amount of audio, and each audio, each sentence have to label with its corresponding transcription. Then with this data, you can train a sequence-to-sequence model. You can train an end-to-end speech recognition model. Then you can do speech recognition. However, the problem is how much data do we need to train a state-of-the-art speech recognition system? I just visited Google, and they told me that they literally collect hundreds of thousands of hours of audio data. And all the audio data has the human transcription. And they use those data to train a system. And the amount of data is more than a human can hear in his or her whole life. So it's very hard to have. If you do not have this kind of data, you cannot compare with Google. So this is, but even for Google, there's an issue. They can collect this amount of data for English, but they are not motivated to collect this amount of data to train the state-of-the-art system for Taiwanese. Because in Taiwan, lots of people speak Taiwanese, but the market is not big enough for them, so they are not motivated to collect a large amount, sufficient supervised data to train a Taiwanese speech recognizer. However, we're considering that can machine learn how to do speech recognition in a completely unsupervised way, just like an infant. Can machine do that? It listen, for example, a Taiwanese family bought the system, and the system always listen to the Taiwanese, can it automatically learn how to transcribe Taiwanese? So this is our vision. So I'm not going to go through the detail, but this is basically the idea. Given the utterance, given a large collection of audio, there are lots of technology that can achieve acoustic pattern discovery. You can discover the common pattern from the acoustic signal. Those patterns can be corresponding to, for example, phoneme or corresponding to words. You can collect lots of patterns corresponding to a specific signal. However, you do not know a pattern, for example, P1 here corresponding to which word or which phoneme, which text. You do not know that. You just know that they corresponding to the same acoustic pattern. On the other hand, it's also pretty easy to collect a large amount of text. Just crawl it from the internet. Then what we want to do is use the technology of GAN. You can transform between these two domains. As I have mentioned, if you have two domains of data, you do not need to pair these two domains of data. Then you can train a transformer from one domain to another. So this is the basic idea. We have audio data. They are represented as pattern. We have text data. Then we want to train a transformation model to transform those tokens into the text. So this is what we want to do. And we do not need the relation. We do not need to label those utterances. Those audio, those text, they do not have to, they don't have to have some relationship. They just come from different sources. Some random audio, some random text. And hopefully, machine can achieve unsupervised speech recognition. So this is what we can achieve now. So what we actually do is phoneme level speech recognition. And the corpus we use, the audio is timid, and the text is WNT. And timid and WNT, they are completely different. So our audio and our text are from completely different sources. And we do not have the relationship between these two domains. We do not label the audio in the timid. We do not use the text transcription of the timid. And this is the result we can obtain. For the blue curve, you found a blue curve here. For this blue curve is the supervised learning approach. So for supervised learning approach, the vertical axis is the accuracy. The horizontal axis is the amount of labeled data we use. Of course, with more and more labeled data, the performance of supervised learning approach is better and better. For the red line and the green line, it's just they are unsupervised approach, but with different technology. I'm not going to go through the detail here. For the red line, it's completely unsupervised, and we achieve 36% accuracy. Probably some people will think 36% accuracy, this is so poor. Probably the output is just not readable. But I have to say that this is the first unsupervised speech recognition system in the world, better than random. So in the previous world, no one has achieved unsupervised speech recognition and get accuracy better than random. And here, the result we obtain is, of course, remarkably better than just random get the result. So I think the time is up. The last part I want to share with you is speech synthesis. I just go through the basic idea very quickly. This slide is kind of complicated. But what I want to show here is in the ancient time, if you want to do voice conversion, you need some pair data. If you want to transform the speech of A to the speech of B, you need the pair audio of speaker A and speaker B. You need to add speaker A and speaker B to alter the same set of sentence. Then you can train the transformation network to transform the audio of speaker A to the audio of speaker B. But this is not the case today. As I have mentioned, based on technology of cycle gain, you can transform between two domains without label data, without the label between these two domains. So what we actually do here is you have the audio of speaker A. You have the audio of speaker B. They are talking about completely different things. You just collect the audio from A, from B, and they are just say completely different thing, but you can train a transformation network to transform between these two domains. Then voice conversion is achieved in this way. So, so this is basically what I want to share with you. And last but not least, the education of deep learning is also important. So I have a YouTube channel teach deep learning technology. And until now, I have 1 million views and 18,000 subscribers. And this is what I want to share with you today. So thank you very much for your attention.
So the TIMIT database is pretty small for speech. Do you anticipate by using much larger corpus that you will improve the performance quite a bit?
Yes, we are going to working on Libre speech. So because we want to see the result first, so we use a very small corpus to verify the idea will work or not. Actually, I believe with much larger database, I believe we will get better performance. We just haven't tried it yet. Actually, literally, we get the result just few weeks before, and we put the result on the archive, so you can check the paper. Thank you very much.
Hi, can you give us some intuition of why cycle gain and letting two chatbots to talk each other won't like overfit to a certain types of conversation? Yeah, thank you.
Okay, so let's talk. So the question you want to ask is, I have mentioned that we can have two chatbots, right? And chatbots can talk to each other and improve each other. Why don't they just find some special way to cheat this task, right? So actually, this is possible. So the task we use is interactive spoken content retrieval to demonstrate the idea. And in spoken content retrieval, you have an agent, which is the retrieval system, and you have a user, which is simulated, but it's learnable. And the simulated user know what it wants to retrieve, but it can only hint the agent. It cannot directly tell the answer to the agent. But probably during the interaction, these two agents find some secret way to communicate to each other, so they can get very good reward in the test. Actually, I believe this is possible. Although in our experiment, we tried to compare the behavior of the learnable user and the real user and found that actually they are quite similar. So we do not think the real user, the simulated user, tried to find some very weird way to cheat the test. But I think probably in some tests, this would be happen. So if this situation happen, I think one possible way is we collect some demonstration from the real user. I think it's hard for the real user to interact with your system millions of times, but it's possible to ask the user to have some demonstration for interacting with your system hundreds of times. Then we probably, during the training, besides the trainable user and the agent, they want to achieve the goal they want to achieve, but at the same time, we want the trainable user that its behavior cannot be too different from the real user. In this way, probably we can give the trainable user more constraint so it will not try to cheat this test. So this is one possible way to prevent cheating in the interaction, to prevent overfitting in the interaction. I hope I answered your question. Thank you.